ÖAW-ACDH Tool Gallery, Generative AI and Vibe Coding. Chapter 1. The History and Development Cycles of Artificial Intelligence. The core idea of artificial intelligence is to transfer human intelligence to computers. This includes replicating the human brain, representing and storing knowledge, interpreting signals from the environment, learning and drawing conclusions, and applying acquired knowledge to new situations. The goal, on the one hand, is to gain a better understanding of how our brain works, and on the other hand, to automate capabilities that we previously considered uniquely human. There are many definitions of AI. The European Union has also enshrined a technology-based definition in the EU AI Act. Andrej Karpathy, co-founder of OpenAI and former director of AI at Tesla, formulated a remarkable idea in his blog post, The Space of Minds. For humanity, LLMs are the first contact with a non-animal intelligence. The only form of intelligence we have ever known is animal intelligence, including our own. AI, and especially large language models, represent a completely new kind of intelligence that has emerged through fundamentally different optimization processes, not through biological evolution and survival, but through statistical simulation of human texts and commercial optimization. In a sense, we have thus created our first alien intelligence, even before encountering extraterrestrial intelligent life. The areas of artificial intelligence are modeled on the human senses and can be divided into input, processing, and output. On the input side stands vision, which in AI is represented by computer vision, the ability to interpret images and videos. Hearing is mapped through speech recognition. Language and sounds are converted into digital data that a computer can process. At the center is thinking, logical reasoning, planning, and learning. This is where the actual intelligence is simulated. The system processes inputs and generates meaningful outputs from them. On the output side, we find robotics, sensing and moving, an area currently growing rapidly, as well as speech synthesis, speaking, the ability to artificially generate spoken language. Together, these areas form the overall picture of AI, from perception through processing to action. When people talk about AI today, it almost all revolves around generative AI, that is, chatbots like ChatGPT, which are based on large language models, LLMs. This is what we call AI tunnel vision. About 90% of public attention is focused on generative AI, although it represents only a small part of the overall AI landscape. The graphic shows the proportions. Generative AI and LLMs form the innermost core. Around them lie deep learning, machine learning, and the entire field of artificial intelligence, with technologies such as neural networks, RNN, CNN, natural language processing, genetic algorithms, and many other approaches. The key message: about 90% of AI techniques lie outside generative AI, especially in fields such as robotics, manufacturing, or image processing. Enormous value creation potential is emerging that has little to do with generative AI. From both a research perspective and for industrial applications, it pays to look beyond this tunnel vision. This slide spans the arc from the beginnings of AI in the 1940s to the ChatGPT breakthrough in November 2022. The main point: AI has an 80-year history that is largely unknown to the general public. In 1943, McCulloch and Pitts published a logical model of the brain, the first mathematical model of neural networks, which to this day is considered the foundation of artificial neural networks. In 1950, Alan Turing proposed the Turing test in his paper Computing Machinery and Intelligence. A machine is considered intelligent if a human interrogator cannot distinguish its answers from those of a human. This test is still used today to assess progress toward AGI, Artificial General Intelligence, and it is also relevant in the EU AI Act as a reference framework for general-purpose AI. On November 30th, 2022, OpenAI released ChatGPT. The product reached 1 million users within 5 days and triggered the current AI hype. Turing's core idea. If a person cannot tell in a conversation whether they are talking to a human or a machine, then the machine is considered intelligent. This principle, the Turing test, is still used today to evaluate AI systems. An impressive example, the DALL-E Lives project at the DALL-E Museum in St. Petersburg, Florida, 2019. Using deepfake technology, Salvador Dali, who died on January 23, 1989, was brought back to life as a lifelike interactive avatar. This shows that even before the ChatGPT hype, AI was capable of producing convincing reproductions of humans. Runway's Turing Real study goes even further. In a test with 1,000 people, 90% of participants were unable to reliably tell AI-generated videos apart from real ones. The key question for you: where do we stand today on the Turing test? How well can we still distinguish between real and machine-generated content? And what questions does this raise about the trustworthiness of AI? The link on the slide leads to the interactive self-test. This slide shows the AI timeline from the 1940s to knowledge-based systems. 3 eras become visible: theoretical foundations, the first hype, and the first practical applications. In the 1950s, the first AI programs emerged. In 1956, the Dartmouth Summer Research Project on Artificial Intelligence took place. A group of researchers around John McCarthy, Marvin Minsky, Claude Shannon, and Nathaniel Rochester coined the term artificial intelligence there as a distinct field of research. Their assumption: every aspect of human intelligence can be described so precisely that a machine can simulate it. This triggered the first AI hype. Researchers were convinced that true machine intelligence would be achievable within a few years. These expectations proved too optimistic, but they led to intensive basic research. In the 1970s, this led to the first practically usable AI systems, knowledge-based systems, also called expert systems, which encoded human expert knowledge into rules and could make decisions within limited domains. Expert systems, also called knowledge-based systems, were the first practical approach to transferring human intelligence to a computer. The core idea: a human expert enters their expertise into the system as facts and rules, essentially cause and effect chains. The system can then draw conclusions in the reverse direction. Starting from an observed symptom, effect, it identifies possible causes and proposes actions. This corresponds to what a physician does, for example: observe symptoms, diagnose the cause, recommend therapy. In this way, the system takes on the role of the expert. Important: the knowledge must be entered manually in advance. The system does not learn on its own. It was precisely this limitation that later led to the development of machine learning. This slide shows a concrete example of how an expert system works, using a legal application. On the right is the legal text as a rule. Anyone who falsely poses as a public official is punished with up to 6 months in prison. On the left, we see the application. Mr. Meyer presents himself as a public official, but is not one. The system automatically infers that an offense has occurred and what punishment applies. The idea was to map the entire legal system into such if-then rules. In practice, this failed for several reasons. A judge must still establish the facts. All laws would need to be formalized and constantly updated. It becomes even more difficult in fields such as medicine, where expert knowledge is rarely as explicit as a legal text. Interestingly, today we are seeing a renaissance of this idea with completely different means. What did not work with rigid if-then rules is increasingly being achieved with large language models. The 2024 study, Better Call GPT, showed that LLMs achieve accuracy in contract review comparable to junior lawyers, at 99.97% lower cost and in seconds instead of hours. Goldman Sachs estimates that up to 44% of legal work steps can be automated. Law firms are already using AI tools for document analysis, legal research, and case file evaluation. The German judiciary is piloting AI use in courts with projects such as Frauke and Akira. The dream of expert systems is thus becoming reality, just not rule-based, but language-based. Despite their limitations, knowledge-based systems are still in use today, wherever safety and traceability are critical. The best-known example, the autopilot in an aircraft. The key advantage, determinism. Given the same input, the system always produces the same result, reproducible and verifiable. If an error occurs, it can be traced precisely. Unlike generative AI, there are no hallucinations. The system works exclusively with programmed rules and invents nothing. The flip side, in unknown situations, the system cannot react, which is why a human remains indispensable as a control authority, human in the loop. In the aircraft, the pilot takes over. In legal practice, the lawyer reviews. As we saw on the previous slide, LLMs today succeed at many things that purely rule-based approaches failed at, but human review remains essential there as well. Or, as the picture sums it up, you can't supervise what you don't understand. That is precisely why we are dealing with the fundamentals here, because automation is not autonomy. Anyone who wants to use AI systems doesn't have to be an expert, but does need to understand the basics of how they work and where their limits lie. This slide extends the timeline with the next eras of AI history. Starting in 1969, the first knowledge-based systems emerged in research, dendral, mycin. In the 1980s, industry recognized their potential. Instead of paying expensive experts, their knowledge was to be formalized in computer systems. However, the industrial uptake ended in the first AI winter, approximately 1988 to 93. The reasons? Experts were not always willing to share their knowledge. Decades of experience were hard to capture in cause and effect chains, and unforeseen situations remained an unsolvable problem. Industry interest declined significantly, but research didn't give up. Instead of abandoning knowledge-based systems, researchers looked for new approaches, and from the 1990s onward, they found them in statistical methods. Instead of entering rules manually, machines were to learn from data. This paradigm shift ultimately led to today's large language models. After expert systems failed, researchers asked the fundamental question anew. What does intelligence actually mean? The starting point, if intelligence arises in the brain, then the computer should take the brain as its model, not rigid rule sets. Fast computation alone is not enough. True intelligence includes learning new things and linking them to existing knowledge, drawing conclusions and generalizing, transferring experience to completely unfamiliar situations, and ultimately, creative activity and self-reflection. An expert system could do none of this. This is exactly where the paradigm shift comes in. Instead of entering rules manually, machines should learn from data, the so-called statistical, learning-based, or stochastic approaches. Different terms for the same core idea, which forms the basis of today's AI systems. Artificial neural networks, ANNs, serve as a representative example of learning-based approaches. The core idea: take the brain's biological information processing as a model. Understand how the brain processes sensory impressions, seeing, hearing, feeling, and generates responses from them. This principle is transferred to the computer. Instead of imposing rigid rules, one builds a system that, similar to neurons in the brain, learns through experience. Understanding the biology helps to create better artificially intelligent systems. This slide answers the core question: what is behind the term artificial neural networks? The approach simulates the way the brain works, but what does that mean concretely? An ANN consists of many small computing units, the artificial neurons, arranged in layers. Data flows through these layers. The first layer takes in the input, e.g. the pixels of an image. The middle layers progressively recognize patterns, first edges, then shapes, then whole objects, and the last layer delivers the result, e.g. cat or dog. Between the neurons lie connections with so-called weights, put simply, adjustment knobs that determine how strongly a signal is passed on. Training works as follows. The network is shown thousands of examples with known solutions. After each example, the system checks whether its answer was correct. If it was wrong, the weights are adjusted slightly, like a child learning through trial and error. After millions of such runs, the network has set the weights such that it is usually correct, even on new, unfamiliar data. Crucially, no one programs the rules. The network finds them itself. The result is a versatile tool: pattern recognition, prediction, and planning, all tasks that were not possible with rigid expert systems. Unlike rule-based approaches, an ANN does not need pre-formulated rules, but learns from data. Exactly how this learning works in detail is shown on the following slides. To understand artificial neural networks, we first need to know their biological model, the neuron. Neurons are specialized nerve cells, the basic building blocks of the brain in humans and animals. Each neuron has three essential parts. The dendrites receive signals from other neurons or from our sensory organs. The cell body, soma, processes these inputs. The axon passes the result via synapses to the dendrites of the next neurons. So the principle is input, processing, output. The threshold is crucial. A neuron only becomes active when the sum of the weighted input signals exceeds a certain value. Not every signal triggers a response. The neuron decides whether the information is strong enough to be passed on. Precisely this principle, weighted inputs, threshold, forwarding, is later modeled mathematically in the artificial neuron. How does signal transmission work? The neuron receives many input signals at the same time. If the weighted sum of these signals exceeds a certain threshold, the neuron becomes active and sends a signal via the axon to all connected neurons. The brain consists of around 86 billion neurons, each connected to about 10,000 other neurons, which yields roughly 100 trillion synaptic connections, synapses. For comparison, parameters in an artificial neural network correspond functionally to synapses. They store the connection strengths between the nodes. GPT-4 has an estimated more 8 trillion parameters. With 100 trillion synapses, the human brain therefore still has about 50 times more connections than GPT-4. A direct comparison of biological neurons with nodes in an LLM is not technically clean, since OpenAI does not publish such architectural details. Computer scientists have tried to recreate this biological principle on a computer. The brain can be understood as a network of neurons, a neural network. Learning means a change in synaptic connections. New experiences change how information is processed and forwarded. Example, when we see a cup, the brain receives visual inputs, shape, color. Based on prior experiences, certain neural pathways activate that recognize the object as a cup and may trigger follow-up actions, e.g. the desire for coffee. This principle, input, weighted processing, output, forms the basis for the perceptron as an artificial reproduction of a neuron. Numerical inputs are given weights, and an activation function computes the output, 0 or 1. On the previous slide, we met the individual perceptron, the artificial version of a neuron. Now we connect many of them into a network. Picture it like this. On the left, the inputs come in, for example, the shape and color of an object. These values flow through several layers of perceptrons, where every connection between two perceptrons has a weight, a number that determines how strongly the signal is passed on. At the end, on the right, The outputs come out, yes or no, 1 or 0. Simple example, you show the network an image of a coffee cup. The input layer receives visual features, round, brown, with a handle. The output layer has several answer nodes. Is it dangerous? 0, no. Is it useful? 1, yes. Can you pour coffee into it? 1, yes. Which outputs are activated depends on the weights, and these are adjusted through training, learning from examples. The technical term for this, directed weighted graph. Directed because the signals only flow in one direction, from left to right, and weighted because each connection has a strength. Here we see a concrete example, a small neural network that computes the XOR function. XOR means either or. The output is 1 if exactly one of the two inputs is 1, but not both at the same time. How to read the diagram? On the left are the inputs A and B, each 0 or 1. These are passed to neurons N1 and N2. Each connection has a weight, a number that determines how much the signal is amplified or attenuated. The neuron sums up all the weighted inputs, sum of output times weight, and compares the result with its threshold. If the sum is greater than or equal to the threshold, the neuron outputs a 1, otherwise a 0. What's special? A single perceptron cannot solve XOR because XOR is not separable by a single straight line. That's why the network needs a hidden layer, N3, that computes an intermediate result. With this additional layer, can the network find the correct answer? This simple example shows the basic principle of all neural networks. Inputs flow through layers of neurons, each connection has a weight, and the weights determine what comes out at the end. In learning, these weights are adjusted so that the network produces the correct results. This slide compares expert systems, symbolic AI, with learning-based systems, non-symbolic AI. Expert systems use logic and symbols. Learning-based systems use examples instead of symbols. Learning. In expert systems, learning is explicit. An expert must be willing and able to share their knowledge and invest a lot of time in doing so. The rules are given to the system directly. In neural networks, by contrast, the weights, connections, activation functions are learned from many examples. The network learns through trial and error how a given input is transformed into the desired output. Similar to how we humans learn from experience, e.g., a hot stove is dangerous. So, implicit learning with examples. Details will follow in 2 weeks. Prediction. In expert systems, rules can be reversed. Reverse cause and effect chain. From an effect, e.g., fever, possible causes can be inferred. Or in a legal case, from a sentence, the offense can be inferred. This is automation based on rules. Learning-based systems, on the other hand, learn patterns from examples and apply them to new data. They find the most similar situation from the past and derive a prediction from it. Errors. Expert systems make no errors within their rule scope, but they cannot cover everything. At some point, they simply deliver no result. Learning-based systems are based on statistics, and therefore also make errors, similar to us humans in new situations. Precision in expert systems. Quality depends on the quantity and correctness of the rules. In learning-based systems, it depends on the quantity and quality of the examples provided. Having seen the differences between symbolic and non-symbolic AI, the question is, how did this develop historically? Why do these two approaches exist, and why do learning-based systems dominate today? The timeline sums everything up. AI spring from the 1990s onward. Precisely because of the advantages of learning-based approaches, statistical methods, not expert systems, were taken up after the AI winter. Researchers recognized that these can respond in unpredictable situations, for example, in robotics. In addition, academic and technical depth grew enormously. Many new techniques emerged, and research activity increased sharply. ChatGPT, November 2022, with the internet as a vast database of examples and large language models as the technique for learning-based approaches. Sam Altman posted about ChatGPT in November 2022. GPT models had already existed since 2018, but ChatGPT as a chatbot application only reached the necessary maturity in 2022. Since then, we have been talking a lot about AI chatbots, but there are many other AI applications. Current developments: LLM-powered RAG systems, retrieval augmented generation, enable knowledge storage and domain-controlled queries. 2026 is considered the year of AI agents with autonomous workflows. Generative AI delivers impressive results in image and video generation. The technical progress is fascinating, but it is unsettling when you can no longer rely on your senses to separate reality from fiction. As a musician, however, enthusiasm prevails. AI-generated popular music is now barely distinguishable from human music, and could put an end to the often poor digital sound quality of recent decades. In the classical music field, it will take a few more years before comparably good results can be achieved. This kind of music is generally significantly more complex and therefore harder to reproduce. The key takeaways: AI has existed since 1943. It is nothing new and nothing to be afraid of. There is great technical and scientific depth that has grown over decades. Many theoretical ideas, such as the Turing test, have proven highly relevant given today's computing power. Two main approaches: symbolic AI, deterministic but with limited usefulness; non-symbolic AI, learning-based systems, many new applications, but non-deterministic and error-prone. Looking ahead, ÖAW-AI, as an Austrian cluster of excellence, is attempting to combine both approaches. Precisely this combination, neurosymbolic AI, is gaining enormous importance. As we learned last week from Roland Fleischhacker, DeepSearch GmbH, his product DeepAssist uses an explicit world model instead of statistics. Transparent, traceable, auditable. LLMs deliver linguistic brilliance. Neurosymbolic AI delivers causality and accountability. The future belongs to the combination of both paradigms. On the other side, Peter Steinberger from Vienna shows with OpenClaw where non-symbolic AI is heading: an autonomous open-source agent with over 178,000 GitHub stars that acts on its own rather than merely responding. Steinberger was recruited by Sam Altman to OpenAI in February 2026. OpenClaw is fascinating, but also a security risk and a glimpse into the future of proactive, autonomous AI agents.